Thank you. Good afternoon, I think, everyone. So I'm going to take you again to the bond stress topic that we discussed earlier. This is a project together with the University of Miami and the University of Sherbrooke in Canada. It's focused on the assessment of development length equation for GFRP rebars in tension. So before we started discussing about the test and the research, for some of you that may not be familiar with the term FRP, FRP stands for fiber reinforced polymers. So it's a composite material made of two different phases, the reinforcement phase, that are the fibers, and the polymer or the resin phase that binds them together, those transferring the stresses between all the fibers and protecting the fibers that have the strength of the composite. So if you mix the fiber with the polymer and some additives, you'll have the FRP composites, typically for structural application. We talk about 4 types of FRPs: carbon, glass, aramid, and basalt. And now that you have the FRP composites, you will have different types of structural elements for internal and external applications. So recently, the ACI Committee 440 issued the new ACI Code 440. That is the first code in mandatory language for the design of structural elements, concrete structural, with GFRP bars. So from now on, I'll be only discussing about GFRP bars. That is the only code that we have right now. Although the ACI Code 1R15 is a guideline that discusses about the other types of FRPs. So why FRP? FRP have a good advantages. Also, it's not a perfect material, have some disadvantages that I'll discuss. So it's a non-corrosive material. So for a specific application, when you want to avoid that corrosion, of course, you will like to have FRP. It's high longitudinal tensile strength. So if you think of a steel that has a yielding strength of 60 KSI, with GFRP bars, you could have a strength of up to 200 KSI. It's lightweight, it's 1/5 of the steel weight. So I'll show you a video that I was able to carry out a cage. So for constructability is also a good advantage. And it's low thermal and electrical conductivity. So for specific applications, you also would like to have FRP. Some of the disadvantages is a material that is elastic up to failure. So for seismic application or some specific application when you want ductility, maybe cannot be the best solution. It's low shear strength and modulus of elasticity, so you have a higher deflection. Typically when you design a flexural element, the serviceability limit states control the design and the ultimate strength. Cannot be bent in field and higher initial cost. I put this in italics because it's not always true. The bend in field, right now we have also thermoplastic resin that can allow the bend in field, and the cost depends on the market. Last year we have GFRP bars that was almost the same price of steel bars, so of course depend on a specific project. If you have a big project, if you discuss with the manufacturer, you could have good prices. And it's longer development length that is associated with the high longitudinal tensile strength and with the characteristics of the surface of the GFRP bars that I will discuss later. So this development length is associated with the bond stresses, how the bonds are being transferred between the rebar and the concrete, and typically are related with the chemical adhesion, friction, or bearing. This bearing is especially true and big in conventional steel rebars when you have those big ribs on the steel, so that allows a better bond. But in FRP bars in general, you have different type of surface treatment. It's not standardized. There is not an ASTM that gives you a specific surface treatment. It depends on the manufacturer. So you could have sun-coated, groove, rib, or helical wrap type of surface deformation, or a mix between them. So here you have like a additional parameter on your equations. So the bond stress and how the bond mechanisms is affecting the bond transfer between the concrete and the rebar is not well established even for steel rebars. There is not a distribution of those bond stress between the rebar and the concrete. So it's a topic that even for steel rebar is not well addressed, and the equation is also a statistical approach, as we will see later. So we want to avoid this bonus failure mode. So typically we could divide those bonus failure between the slippage failure, that is when the bar slips from your element, and splitting failure, that is a more complex type of failure because you have more parameters like the clear concrete cover, the tensile strength, the rebar diameter, the confinement effect. So you have more parameters that could affect those splitting and, as I mentioned, the surface treatment of your FRPs. Of course, the one that you would like is the tensile failure. You want to achieve the full capacity of your rebar. So here I have the two equations, the one from ACI for steel, the ACI 318, and the ACI 440, the one that is in the code. Both equations come from a statistical approach. It's a two-parameter linear regression, so it doesn't have a physical meaning behind it. It's not like a mechanical approach. It's a statistical approach. They plot the data that they gathered. The equation for steel was developed in 1986, something like that, and the one from GFRP was developed in 2006. So there are two old equations, but for steel, we have not changed the steel a lot. But for GFRP rebars, we have different type of generation of rebars. So some authors in some studies have stated that this equation could be over-conservative. Others have said that it could be not enough conservative for our applications. So this equation was developed using the first generation of FRP rebars, was developed almost 20 years ago. Some conservative assumptions were made. Some parameters were disregarded. In the equation for GFRP, we don't consider the confinement effect of the stirrups. Some authors have conducted some research, but with the steel stirrups. But of course, the ACI code 440 only allows the use of GFRP stirrups. And there have been significant improvements in FRP materials. We're now talking about the second generation of GFRP rebars. So different modulus of elasticity, different ultimate strength. So we saw the different codes and guidelines that are available, the ACI 440, the Canadian code, the Japanese code. So we try to address the most parameters that we could. So in this study, we're trying to test almost 70 beams to address the different parameters that I'll discuss. So we want to determine the development length of GFRP rebars, assess the different effects of the parameters, and also in GFRP, you could have two different types of approach. Could be compression control section or tensile control section. Not usually as steel, there is a tensile control section. When your concrete crush, the steel rebar yields. In this case, for GFRP, you could have both. Usually the compression control section with serviceability limited states control your design. So you will have two phases, one phase with compression control section, another one with tensile control section. So this is the methodology. We're casting almost 70 beams with 300 millimeters wide, 450 depth, and 5 meters long. So this is a scheme of those beams that we are testing at the University of Sherbrooke in Canada. So this is the graphical abstract, so a 4-point bending test to have a constant moment region, different parameters, the concrete compressive strength, the GFRP bar diameter, the clear cover, confinement effect with the stirrups rebar, and the splice length that, of course, we want to discuss. The data collection, of course, the deflection, failure mode, strain gauges, and we install some small potentiometers inside of the rebar to measure that slippage and know if the bar is moving to classify that as a slippage failure. And of course, the next phase will be the data and gather all that information. So we are working with 3 different types of splice length. If you compare the splice or the development length with the equation, the currently equation, you will get 110 dB. So this is almost 2 meters of splice. So for constructability or detailing, if you need to splice 2 meters of that GFRP rebar, that could cause some issues in your work. So for the instrumentation, LVDTs, strain gauges, the internal strain gauges, we'll try to be very careful to not to break the bone, because if we are measuring the bone and we are breaking when we are installing the strain gauges, of course we are losing that that bone. We notch the beam to force the first cracks at the exact location of the splice. As I mentioned, we installed some small potentiometers, so we made a hole on the rebar, and we installed a small potentiometer there. Of course, we covered that potentiometer to avoid any damage when pouring the cast, the concrete. So this is the cages that I mentioned. It's a 5 meters beam. I was able to move that cage by myself. If this was being full steel, I will need the forklift to move. So one of the advantages is the lightweight of the GFRP. Another extra video. So this is the notch, the pouring of the concrete. As I mentioned, when we install the strain gauges, we try to be very careful to not to break the bone. So we try to damage the lesser possible. The loading protocol is a 4-point bending test, displacement control to measure the if we have some inelastic deformation there. So this is this one of the tests we are currently doing. It's not at finishing research. So we want to classify the failure. So in this case, of course, it's a splitting failure. You have that splitting crack. This will be more like a slippage failure because you only have that big crack, but you don't have any horizontal crack, so it's not a splitting failure. So we want to classify both because the current equations are only based on splitting failure mode. Usually the slippage failure modes are avoided in the requirements by establishing a minimum embedment length, and the splitting failure, that is a more complex process, are with the equations. So this is a typical, this is one of the beams that we already test. If you can see here, I plot the FMN. So if you would like to design this beam, the FMN is around 400 inches keep, but the maximum capacity of the beam is almost twice that. So of course, if you would like to design that beam, you are always on the safety region on that one, and the beam could develop twice the capacity, because in this case it's a tensile control section, and the code works with a strength reduction factor of 0.55. So you are reducing the 45% the capacity of your beam. So what is next? We would like to really understand how that bond is working, how is the mechanisms of transferring the stresses, because of course if you have the cracks in one crack, you have the full the rebar is taking the full stresses, but the rebar wants to transfer that stresses again to the concrete. So if you have more or less cracks, that will affect the way how the bond is working, and of course that affect on the effective development length. So usually previous studies, when they compute the bone stress, they just take the average. It's a reasonable way to do it, but it's maybe not that it doesn't take into account the real behavior and the real mechanisms of the bone stresses. So we want to finish all the tests. It's a research in progress still. After that, and all the data that we already gathered, we want to update or propose a new equation that have more mechanical background, and not simply a statistical that plot the data, and the equation that we got, that's the data, but give the designers a more understandable equation. So this is the part that I have so far. I hope in the upcoming convention have a final version of this research in progress. Thank you.